ground fault protection of equipment, GFPE, that's causing nuisance trips on a 120/208 volt solidly grounded wire electrical service is a frustrating problem. Let's explore the potential causes and solutions. Firstly, the nuisance tripping could be caused by an incorrect setting. The GFPE might be set with too high of sensitivity, leading it to trip even under normal operating conditions. Secondly, the problem could be a ground fault. An intermittent or permanent ground fault somewhere downstream in the electrical system could be triggering the GFPE. To solve the tripping issue, it's important to determine the root cause. If the setting is too low, increasing the GFPE setting to a more appropriate level could resolve the issue. Be sure to stay within the manufacturer's recommended range for the GFPE settings. If there is a ground fault, using a ground fault locator to pinpoint the precise location of the fault is crucial. Repairing or replacing any damaged equipment or wiring that's causing the ground fault is essential. Upgrading the electrical system to a higher fault current rating may also be considered, especially if the ground fault is intermittent and difficult to trace. If the GFPE is deemed unnecessary, consider that the National Electrical Code, or NEC, typically does not mandate GFPE on a solidly grounded 120/208 volt service. Disabling or removing the GFPE would get rid of the nuisance trips. It's important to remember that GFPEs offer supplementary protection against electrical hazards, specifically in damp or wet environments. Here are some recommendations. Perform a performance test on the GFPE to ensure it's operating correctly. Conduct a thorough ground fault investigation using a ground fault locator to identify any existing ground faults. Only disable the GFPE if there's no evidence of ground faults and the nuisance trips are causing significant disruption. Reevaluate other safety measures. Make sure alternative safety measures are in place, such as regular inspections and ground fault circuit interrupters, GFCIs, on individual circuits, to minimize the risk of electrical hazards. Now let's delve deeper into the technical aspects. A GFPE system monitors the balance of current flowing through the phase conductors and the neutral conductor. In a healthy system, the current flowing into the equipment should equal the current flowing out. If a ground fault occurs, some current will return through a path other than the intended circuit conductors, creating an imbalance that the GFPE detects. The GFPE then trips the main circuit breaker to de-energize the circuit and prevent further damage or injury. The sensitivity of a GFPE is typically adjustable, allowing you to set the level of imbalance that will trigger a trip. If the sensitivity is set too low, even small, normal leakage currents can cause nuisance trips. Conversely, if the sensitivity is set too high, the GFPE may not trip in the event of a true ground fault, compromising its protective function. When adjusting the GFPE settings, it's important to consult the manufacturer's instructions and consider the specific characteristics of the electrical system. Factors to consider include the size and type of load, the length of the circuit conductors, and the presence of any sensitive electronic equipment. In addition to adjusting the GFPE settings, it's also important to inspect the electrical system for any potential sources of ground faults. Common causes of ground faults include damaged insulation on conductors, loose connections, and moisture intrusion. A ground fault locator is a valuable tool for identifying the location of ground faults. This device injects a signal into the circuit and then traces the signal along the conductors until the fault is located. Once the ground fault is identified, it should be repaired or replaced immediately. If the GFPE is deemed unnecessary and is to be disabled or removed, it's important to ensure that alternative safety measures are in place. GFCIs are a proven technology for protecting against electrical shock hazards. GFCIs should be installed on all circuits serving wet or damp locations, such as bathrooms, kitchens, and outdoor areas. Regular inspections of the electrical system are also essential for identifying potential hazards before they cause problems. During these inspections, look for signs of damaged insulation, loose connections, and moisture intrusion. Any identified hazards should be addressed promptly. It is important to understand the different types of ground faults. A bolted ground fault is a direct connection between a phase conductor and ground. This type of fault typically results in a high fault current and a rapid trip of the GFPE. A high-resistance ground fault is a connection between a phase conductor and ground through a higher resistance. This type of fault typically results in a low fault current and may not be detected by the GFPE if the sensitivity is set too low. An intermittent ground fault is a ground fault that occurs intermittently. This type of fault can be difficult to troubleshoot because it may not be present when the electrical system is being inspected. In addition to the GFPE, there are other types of ground fault protection devices available. A ground fault circuit interrupter, GFCI, is a device that protects against electrical shock hazards by detecting ground faults and interrupting the circuit. GFCIs are typically installed in bathrooms, kitchens, and outdoor areas. A ground fault relay, GFR, is a device that protects equipment from damage due to ground faults. GFR are typically used in industrial and commercial applications. The NEC provides specific requirements for ground fault protection of equipment. Section 230.95 of the NEC requires ground fault protection of equipment for solidly grounded wire electrical services of more than 150 volts to ground but not exceeding 1000 volts phase to phase for each service disconnecting means rated 1000 amps or more. There are exceptions to this requirement, such as for fire pumps and critical operations power systems. The purpose of ground fault protection of equipment is to reduce the likelihood of damage to equipment due to ground faults. Ground faults can cause overheating, fires, and explosions. It is essential to understand the coordination of overcurrent protective devices. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. When coordinating overcurrent protective devices, it's important to ensure that the device closest to the fault will trip first. This will minimize the amount of damage to the electrical system. The time current curves for overcurrent protective devices show the amount of time it takes for the device to trip at different levels of current. When coordinating overcurrent protective devices, these curves should be reviewed to ensure that the devices are properly coordinated. Selective coordination is a design approach where the overcurrent protective devices are coordinated so that only the device closest to the fault will trip, minimizing the impact on the rest of the electrical system. This requires careful selection and setting of the overcurrent protective devices. Understanding the different types of electrical noise is important for troubleshooting nuisance tripping problems. Electrical noise can interfere with the operation of electronic equipment and cause nuisance trips of GFPEs. Common sources of electrical noise include lightning, switching transients, and electromagnetic interference, or EMI, from other equipment. Shielded cables and filters can be used to reduce the impact of electrical noise on electronic equipment. Switching transients are momentary surges of voltage or current that can occur when electrical equipment is switched on or off. These transients can cause nuisance trips of GFPEs. Surge protective devices, or SPDs, can be used to protect electronic equipment from damage due to switching transients. Harmonic distortion is a type of electrical noise that can be caused by nonlinear loads such as electronic ballasts and variable frequency drives. Harmonic distortion can cause overheating of electrical equipment and nuisance trips of GFPEs. Harmonic filters can be used to reduce the level of harmonic distortion in an electrical system. Power quality monitoring is a process of measuring and analyzing the characteristics of electrical power. Power quality monitoring can be used to identify and diagnose power quality problems such as voltage sags, voltage swells, and harmonic distortion. Power quality monitors can also be used to track the performance of electrical equipment and identify potential problems before they cause failures. Insulation resistance testing is a method of measuring the resistance of the insulation on electrical conductors. Insulation resistance testing can be used to identify damaged insulation, which can be a source of ground faults. A megometer, also known as a megger, is a device used to measure insulation resistance. Thermography is a method of using infrared cameras to detect temperature differences in electrical equipment. Thermography can be used to identify overheating components, which can be a sign of a potential problem. Regular thermographic inspections can help to prevent electrical failures. Vibration analysis is a method of measuring and analyzing the vibrations of rotating equipment, such as motors and generators. Vibration analysis can be used to identify imbalances, misalignments, and other mechanical problems. Regular vibration analysis can help to prevent equipment failures. Lastly, consider these safety precautions. Always to energize electrical equipment before working on it. Use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Follow all applicable electrical codes and safety standards. If you are not qualified to work on electrical equipment, contact a qualified electrician. When working on electrical systems, it's crucial to have a thorough understanding of grounding and bonding. Grounding provides a low impedance path for fault current to return to the source, allowing the overcurrent protective device to trip and clear the fault. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the potential for voltage differences and electrical shock hazards. The NEC provides detailed requirements for grounding and bonding in Article 250. These requirements cover everything from the size of grounding conductors to the methods of bonding metal enclosures. Proper grounding and bonding are essential for electrical safety and for the reliable operation of electrical equipment. Remember to always refer to the latest edition of the NEC and local electrical codes for specific requirements. Consulting with a qualified electrical engineer or electrician is highly recommended for complex electrical systems or when troubleshooting persistent problems. The information presented here is for general guidance only and should not be considered a substitute for professional advice. Electrical work can be dangerous, and it's crucial to prioritize safety at all times. When troubleshooting GFPE tripping issues, a systematic approach is essential. This involves gathering information about the problem, inspecting the electrical system, testing components, and analyzing the results. By following a logical process, you can effectively identify the root cause of the tripping and implement the appropriate solution. Remember to document all of your findings and actions. This will help you track your progress and provide a valuable record for future reference. Good record keeping is essential for maintaining a safe and reliable electrical system. In conclusion, solving nuisance GFPE tripping on a 120/208 volt service requires a combination of technical knowledge, troubleshooting skills, and a commitment to safety. By understanding the potential causes of tripping, following a systematic approach to troubleshooting, and implementing appropriate solutions, you can resolve these issues and ensure the safe and reliable operation of your electrical system. Remember to always prioritize safety and consult with qualified professionals when needed. Electrical systems are complex and potentially dangerous, and it's crucial to have the expertise and experience to work on them safely. With the right approach, you can effectively address GFPE tripping issues and maintain a safe and reliable electrical environment.